This is the second part of Part 18 of the LEED V4 Reference Guide for Homes Design and Construction Online Review. Again, all the pictures or images in this video are from Google and USGBC website. If you have comments, suggestions or complaints regarding the images, pictures or in this video, please email me at nelca_roco@yahoo.com, and I will immediately reply to you and take action on whatever the reason of your email. Thank you. Why I created this online reviewer. To help myself and others to pass the LEED AP exam in one shot. These are the LEED credit categories. On my previous video, we discussed the Energy and Atmosphere Prerequisite 1, the Minimum Energy Performance Part 1, now we will continue this same credit due to its long presentation. Energy Cost Savings. For EA Prerequisite Minimum Energy Performance and EA Credits Annual Energy Use, modeled energy savings must be reported on an energy cost basis using actual utility rates or the state's average energy prices. Using energy cost savings as a metric for overall building energy efficiency is important for several reasons. It aligns with the energy modeling procedures in ASHRAE 90.1/2010, Appendix G, and provides a uniform metric for all fuel types. It captures the relative effects of various efficiency measures on energy demand and long-term operating costs, valuable metrics for the owner in determining the overall cost-effectiveness of selected efficiency strategies. And finally, the energy cost savings metric can help designers understand energy consumption because in many cases, cost and carbon emissions of each fuel source are closely correlated. Exceptional Calculation Method. In ASHRAE 90.1/2010, Appendix G, Section G2.5, an Exceptional Calculation Method, ECM, is used when the simulation program that is generating the energy model is incapable of modeling a certain design, material, or device of the proposed design. LEED has adopted and slightly expanded use of exceptional calculations to cover any savings claimed for a non-regulated load, defined as any building load, end use, or control without an Appendix G baseline modeling requirement that allows the load, end use, or control to be modeled differently in the proposed and baseline buildings. Energy savings limitations. Section G2.5 indicates that exceptional calculation methods cannot constitute more than half of the difference, that is, savings, between the proposed and baseline buildings. This will be enforced for the ASHRAE definition of an ECM. However, in LEED, this rule will not be applied to savings attempted on non-regulated loads unless the non-regulated load cannot be modeled in the simulation program. Elements that cannot be simulated by modeling program. One type of ECM is creating a representation of an element that cannot be modeled directly by the chosen energy modeling software. Examples include innovative external shading devices, underfloor air systems, and the heat recovery performance of a variable refrigerant flow system. Whether a particular strategy is considered an ECM may depend on the modeling program and whether the energy modeler can simulate an approximation of the system in the software. If the methodology for approximation has not been previously published by ASHRAE or USGBC as an acceptable modeling path, it is the responsibility of the energy modeler to submit a narrative explanation describing the simulation and providing the calculations for the energy savings if necessary. Documentation for non-regulated loads. Examples of non-regulated load savings include manufacturing equipment not regulated by 90.1/2010, a unique manufacturing process, or any refrigeration or kitchen equipment, including operation, not specifically covered in the LEED Retail Rating System Appendix 3, Tables 1-4. Energy savings for non-regulated loads require additional documentation. ASHRAE 90.1/2010, Table G3.112, indicates that variations of the power requirements, schedules, or control sequences are allowed by the rating authority, provided the proposed design represents a significant verifiable departure from documented conventional practice. Project teams must document the following information to prove that the savings represent a departure from conventional practice and are not required by local code. A narrative describing all baseline and proposed assumptions. the calculation methodology used to determine the savings. A document verifying that the efficiency measure is not conventional practice. This is generally accomplished either by documenting the baseline comparison system/schedule/control as standard practice, or by showing that the savings claimed for the efficiency measure are incentivized by a local utility program. Examples of documents used to verify that the efficiency measure is not conventional practice may include the following. 1. A recent study with research tabulations or monitored data establishing standard practice for the given application in similar newly constructed facilities. 2. A new construction utility or government program that provides incentives for the measure. 3. A document showing the systems used to perform the same function in similar facilities built within the past 5 years. These systems are treated as the baseline system in the analysis, and evidence must show how the energy used for the baseline and proposed buildings is determined. Alternatively, the project team may use any of the prescriptive requirements from ASHRAE 90.1/2010 as the baseline requirement without further justification to substantiate conventional practice, but only for the specific component. Additional guidance. Sources of typical efficiency measures include the ComNet manual, which has a calculation methodology for determining savings for process or receptacle loads, especially savings from Energy Star equipment. These are offered in Section 6.4.5, Receptacle and Process Loads, and Appendix B. Always provide a narrative explanation of the methodology used to calculate savings for exceptional calculation methods. Separate calculations are not necessary when the energy saving are found easily in the modeling results. Most common items in residential spaces are called out in USGBC's Residential Energy Modeling Guidance. Changes from earlier versions of ASHRAE and LEED. Some efficiency measures that no longer need to be modeled using an exceptional calculation method include garage fan demand-controlled ventilation, low-flow water fixtures, kitchen equipment, and kitchen ventilation. Enclosed parking garage ventilation. Modulating fan airflow rates based on contaminant levels are now required to be installed, unless certain exceptions apply, per Section 6.4.3.4.5. Any design that goes beyond these minimum baseline requirements may be counted. 2 factors can affect the energy consumption. 1. The baseline fan power, and energy per flow, must be consistent with the proposed installed fan power at full load conditions. The project team may count higher fan motor efficiencies in the proposed building. 2. The ventilation rate, and thus fan power, could also be reduced if the project team's design allows the fans to reduce the ventilation rate below 50%. The baseline ventilation rate must be set at the minimum requirements of ASHRAE 62.1/2010, which is 0.75 CFM per square foot, 3.8 liters/s per square meter. This must be the baseline ventilation rate, regardless of any local code. The same requirements apply to demand-controlled ventilation for outdoor air control sequences that provide ventilation for building occupants. Low-flow service water heating fixtures. The flow rates given in WE prerequisite indoor water use reduction set the allowable baseline values. Provide sufficient information to justify energy savings from efficient fixtures and appliances that use hot water. Kitchen equipment. All project types may count energy savings from efficient refrigeration equipment, cooking and food preparation, clothes washing, and other major support appliances. LEED Appendix 3, Retail Tables 1-4, defines the baseline conditions. Provide sufficient information to justify all the savings. Savings for a piece of equipment, or its operation, not covered in Appendix 3 must be modeled using the ECM described above. Kitchen ventilation. ASHRAE 90.1/2010 now addresses kitchen ventilation, so it is no longer considered an unregulated load. Section G3.1.1, Exception, D, requires a kitchen with more than 5,000 CFM, 2,360 liters/s, of total exhaust airflow to be modeled with its own separate system. Include demand ventilation on 75% of the exhaust air, and reduce exhaust and replacement air by 50% for half the kitchen occupied hours in the baseline design. Additionally, the maximum exhaust flow rates for hoods must meet the requirements of Section 6.5.7.1.3. The exhaust flow rate must be modeled identically in the baseline and proposed case at design conditions unless Appendix G indicates otherwise. Any design that goes beyond these minimum baseline requirements may be counted. Provide sufficient information to justify all kitchen ventilation savings, with consistent assumptions and operating schedules. Project teams that count kitchen ventilation savings must separate the savings from each end use, for example, fan, heating, cooling, when reporting the energy outputs. ASHRAE 90.1, 2010 versus 2007. The reference standard for building the baseline model for this prerequisite has been updated to ASHRAE 90.1 to 2010, which represents a substantial increase in efficiency from the previous version, ASHRAE 90.1 to 2007. The major changes are described in Tables 1 and 2. Table 1. Comparison of ASHRAE 90.1 mandatory requirements, 2007 and 2010. Table 2. Comparison of ASHRAE 90.1 prescriptive requirements, 2007 and 2010. Common issues with energy modeling. Thoroughly review both ASHRAE 90.1 2010 and the 90.1 2010 User's Manual. The manual presents extended explanations and also includes examples of the concepts and requirements within the standard. Table 3 addresses many of the most common issues but is not a comprehensive list. Modeling considerations. Retail. For projects using whole building energy simulation, include all relevant process loads in the energy model and ensure that they are modeled accurately. Typical retail process loads include refrigeration equipment, cooking and food preparation, ice machines, display lighting for merchandise, clothes washing, and other major support appliances. Compare the energy consumption of each piece of equipment with the value indicated in Appendix 3, Tables 1 to 4. If the item is not included and the project team wishes to take credit, the exceptional calculation method must be followed. For hardwired refrigeration, the modeling software may be used if the system can be modeled explicitly. Otherwise, a thermodynamically similar component model must be used, in accordance with Table G3.1.13. An example of this would be an analysis prepared using 8,760 hourly weather data. For commercial kitchen equipment and refrigeration defined in ASHRAE 90.1 2010, Appendix 3, Tables 1 to 4, no additional documentation is necessary to substantiate these predefined baseline systems as industry standard. Supporting documentation is still needed to verify that the proposed equipment includes the claimed energy-efficient features.
District Energy Systems. Projects that are served by District Energy Systems, DES, should demonstrate compliance with EA Prerequisite Minimum Energy Performance and EA Annual Energy Use by following one of the following methods. The project team may choose Path 1 ASHRAE 90.110 Appendix G, Path 2 Full Day Performance Accounting, or Path 3 Streamlined Day Modeling. The modeling path chosen by the project team may depend on the relative efficiency of the day to which the project is connected, how much day information is available, or whether an energy model already exists for the system. Scope of day equipment inclusion. All downstream equipment must be included in the scope of EA Prerequisite Minimum Energy Performance and EA Credit Optimize Energy Performance. Downstream equipment includes heat exchangers, steam pressure reduction stations, pumps, valves, pipes, building electrical services, and controls. Upstream equipment is included or excluded depending on the chosen option and path. Energy simulation versus post-processing. Whenever possible, incorporate system and equipment performance parameters directly into the energy simulation. Potential methods include developing efficiency curves and scheduling equipment operation and curves. Post-processing of day performance is acceptable if reasonable simulation methods are not available or are too onerous. All post-processing methodologies must be fully documented. Path 1. ASHRAE 90.1 to 2010, Appendix G. Model the proposed and baseline designs using purchased energy according to ASHRAE 90.1 to 2010, Appendix G. Energy rates. All virtual day energy rates must be identical in the baseline and proposed cases. If tariffs or rates are not available from the district plant serving the project, such as for campus or military plants, calculate the rates based on the virtual electric and fossil fuel rates from the model. If a flat rate structure, in which the cost per unit of energy is the same throughout the year and there are no demand charges, is being used for all energy sources, then those flat rates become the virtual energy rates for the project. If all energy rate structures are not flat, a preliminary run of the Option 1 baseline case energy model must first be completed to identify the virtual electric and fossil fuel rates for the project. For this preliminary run only, the rate for the day supplied energy may be left blank or entered as any value. Once all the virtual energy rates are known for electricity and fossil fuel, calculate the virtual day rates for both the baseline and proposed case. Exception: to obtain the virtual fuel rate when the connected building does not use fossil fuel but the day central plant does, use a flat rate consistent with the central plant rates or the historical average local market rates. No preliminary model run is needed. Input the virtual day rates into the modeling software for each day source and use for the remainder of the process. Alternatively, calculate the day energy costs directly by multiplying the day energy consumption for each day source by its virtual day rate. Path 2. Full day performance accounting. Path 2 is available to projects connected to day that wish to account for average efficiency across a smaller time step. The energy model scope accounts for both downstream equipment and upstream equipment and requires calculation of the district energy average efficiencies using either modeling or monitoring. Energy rates. All day energy rates must be identical in both the baseline and the proposed cases. Use local rates as they would normally apply to the building for the energy sources under consideration. For energy sources used by the day but not normally available to the building, such as diesel fuel, use the rates charged to the day. If this information is not available, use representative market rates. Exception: for day plants that operate under specific and atypical rate structures and actively take advantage of those rates through strategies such as load management or energy storage, use the rate structures as they apply to the day. Baseline building plant. Model the baseline case with an on-site plant that is compliant with ASHRAE 90.1 2010, Appendix G, baseline requirements for site-generated thermal energy. Model the baseline building plant with conventional equipment using performance parameters and efficiencies per ASHRAE 90.1 2010, using energy sources corresponding to the day. Proposed building plant. Model the proposed case with a virtual day equivalent plant. Model a virtual plant with the same efficiencies as the entire upstream day heating, cooling, and combined heat and power (CHP) systems, including all distribution losses and energy use. Equipment efficiencies, distribution losses, and distribution pumping energy may be determined using any of the following methods. Monitored data. Engineering analysis. Default values. Efficiencies and losses may be determined and modeled at any level of time resolution, from hourly to annual. However, the time resolution must be sufficiently granular to capture and reasonably represent any significant time or load-dependent interactions between systems, such as thermal storage or CHP. Monitoring and analytical methods may be combined as necessary and appropriate. Monitoring data for heating, cooling, pumping, and cogeneration may be used only if the thermal loads that are monitored represent at least 90% of the load on the campus or district plant predicted after building occupancy. Whether using monitoring or an analytical method, the methodologies must be fully documented. The following specific requirements apply. Heating and cooling plants. Efficiencies, whether determined through monitoring or analytically, must include all operational effects, such as standby, equipment cycling, partial load operation, internal pumping, and thermal losses. Thermal distribution losses. Use monitored data or an engineering analysis. Monitored data determine the distribution losses for the day by measuring the total thermal energy leaving the plant and comparing it with the total thermal energy used by the buildings connected to the day. Rate the plant efficiency accordingly in the energy model. Plant efficiency, percent, x, 100%, distribution loss, percent. An engineering analysis takes into consideration all distribution losses between the day and the building. For distribution main losses, use a prorated amount based on load. For dedicated branch losses, use the total losses of the branch that feeds the building, including heat losses and steam trap losses. Compare the total losses with the total load of the building to get a percentage distribution loss relative to load and downgrade the plant's efficiency accordingly in the energy model. Pumping energy. Whether through monitored data or engineering analysis, determine pumping energy for the project by prorating the total pump energy of the day by the ratio of the annual thermal load of the building to the total annual day thermal load. Model the pump energy as auxiliary electrical load. Pumping energy must be determined or estimated where it applies, that is, there is no default value. Default efficiencies and losses. Actual efficiency performance data on the day serving the project building is preferred. If the project team cannot obtain or determine the actual performance data, use the following default values. These values are conservative and are intended to represent a day with relatively low efficiency. A well-designed, well-operated day generally performs better. Day heating plant, 70%, higher heating value, HHV, for the total boiler plant average efficiency. Day cooling plant, coefficient of performance, COP, of 4.4 for the total cooling plant average efficiency, including cooling towers and primary pumps. Thermal distribution losses including minor leaks or condensate losses. 1. Chilled water district cooling, 5%. 2. Hot water district heating, 10%. 3. Closed loop steam systems, 15%. 4. Open loop steam systems, 25%. For steam systems that are partially open and partially closed, prorate between the above 15% and 25% losses in accordance with the fraction of expected or actual condensate loss. The above guidance assumes that day-generated heat is used for heat in the connected building, and day-generated cooling is used for cooling in the connected building. If the day produces heating that is then converted to cooling for the connected building using absorption chillers or other similar technology, this guidance must be modified. See CHP modeling guidance. Path 3. Streamlined day modeling. Path 3 is applicable for simple district energy systems. The energy model scope accounts for both downstream equipment and upstream equipment and also requires calculation of the district energy average efficiencies using either modeling or monitoring. Energy rates. Use the streamlined day modeling in the calculator provided by USGBC to allocate the energy costs to the results of the model for each district energy source, in lieu of the purchased energy rates, to determine the baseline and proposed case energy costs. Baseline building plant. Calculate the average annual efficiency values for each district energy fuel source used to generate and distribute the thermal energy based on ASHRAE 90.1 2010, Appendix G, baseline case requirements. These values depend on the ASHRAE 90.1 2010 system type that would be selected for the building if the baseline case were modeled with on-site equipment. The calculations for baseline cost per district energy source are the same as those for the proposed case model, except that the average efficiency is constant. Proposed building plant. Determine a single value for average annual efficiency, including thermal losses and distribution energy, for each district fuel energy source used to generate and distribute the thermal energy. For example, for chilled water. CHP modeling guidance. The baseline case is modeled as described in ASHRAE 90.1, Appendix G, and as summarized in the steps for each path. The baseline model assumes separate production of electricity and thermal energy. Although not modeled as CHP, the baseline case is charged with extra energy use for CHP energy accounting purposes in some situations. The proposed case may be modeled in various ways. The average electricity generation, fuel input, and heat recovery of the CHP must be determined, or the defaults for electric and thermal efficiency, below, must be used in conjunction with capacity ratings of the equipment. Calculate annual electricity generation using one of the following methods. 1. Monitor the total annual gross electricity generation. Also monitor the total annual parasitic loads, such as the annual electricity used for cooling the intake air for a turbine. Calculate the net annual electricity generation by subtracting all parasitic loads from the annual gross electricity generated. 2. Model the generators in energy simulation software per Appendix G. Use peak electricity efficiencies and generator curves that match the installed generators. Apply measured or estimated load profiles as process loads to reflect the estimated total electric and thermal loads on the district energy CHP system. Use the total energy generated and total fuel input from this analysis. Any parasitic loads must be included in the analysis and subtracted from the annual electricity generation. Calculate annual fuel input using one of the following methods. 1. Monitor the total annual fuel input to the generators. 2. Model the generators in energy simulation software per Appendix G. Use peak electricity efficiencies and generator curves that match the installed generators. Calculate waste heat recovery using one of the following methods. 1. Monitor the total waste heat recovered. 2. Model the generators in energy simulation software per Appendix G. Use peak electricity efficiencies and generator curves that match the installed generators. Model the thermal equipment served by the CHP waste heat, such as boilers and absorption chillers, using the installed equipment capacities, efficiencies, and efficiency curves, and reflecting the total heating and cooling loads on the plant as a process load. Use the energy modeling outputs to identify the total heat recovered. For baseline CHP electricity output, follow the general procedures described in this section for the proposed case, and adjust the results as follows depending on the results of the day electricity allocation and the total modeled electricity use of the building in the Path 2 or Path 3 proposed case, including the electricity consumption of district plant equipment serving the building. Scenario A. If the building's allocation of CHP generated electricity is less than or equal to its modeled electricity consumption, no adjustment is necessary. The baseline building is charged with the energy used by its non-CHP systems at market rates using standard procedures. Scenario B. If the building's allocation of CHP generated electricity exceeds its modeled electricity consumption, the amount of excess CHP electricity allocated to the building is considered process energy in the energy model. Adjust the input fuel associated with this excess CHP electricity in the baseline case as described in CHP fuel input. For the proposed design CHP electricity output, allocate the electricity generation to the building based on the fraction of thermal loads to the building for the day sources that use recovered waste heat. For each day source supplied to the building, determine the fraction of the recovered waste heat applied to that source as well as the amount serving the project building. For relatively simple day systems, in which the recovered waste heat is used directly in the day, and for which waste heat serves only heating loads in the connected buildings, use the formula for simple systems. For CHP plants in which a portion of the recovered heat is used to drive absorption chillers that provide cooling through a day chilled water loop, or a portion of the recovered heat is used for a third, separate district energy source, for example, if the building connects to both a steam loop and a hot water loop, Calculate the electricity generation assigned to each building using the formula for heat recovery-driven chillers. When modeling CHP fuel input, allocate the CHP input fuel to the project building based on a proration and assignment of the total input fuel according to the results of the CHP electricity allocation described above for CHP electricity output. Use the prevailing energy rates as they apply to the project. Any additional energy used by the proposed design is also charged at market rates. For the proposed case, all projects, calculate the CHP input fuel allocated to the building as follows. For the baseline, scenario B and CHP electricity output only, calculate the CHP input fuel allocated to the building as follows. The model must include CHP generator default efficiencies. Actual efficiency performance data on the CHP serving the project building is preferred, based on either ongoing operations, existing CHP, or design specifications, new CHP. If the project team cannot obtain the actual performance data, use the following default seasonal performance values. These values are conservative, intended to represent a CHP system with relatively low efficiency. A well-designed, maintained, and operating CHP system will generally offer better performance than the defaults listed below. Generator electrical efficiency, 22%. Generator thermal efficiency, 25%. Single effect absorption chillers, 0.60 COP. Double effect absorption chillers, 0.90 COP. Absorption cooling plant electrical efficiency, including cooling towers and primary pumps, 40 COP.
Special situations for DES energy models. Service water heating. If service water is heated in full or in part by DES supplied heat, consider modeling the energy source as purchased energy to hold the DES cost neutral for service water heating. If desired, project teams using Path 2 or Path 3 may use an exceptional calculation method to document DES-related savings from service water heating. Project teams that elect to document savings must fully justify and support the annual energy consumption and cost in both the baseline and the proposed models. Use a reasonable, well-founded purchased energy rate in the models, such as the actual rate paid to the DES supplier or virtual rate. Heating converted to cooling. Sometimes the district or campus system heating energy supply is converted to chilled water using absorption chillers or other similar technologies to serve cooling loads. In this circumstance, the equipment that converts heating to cooling may reside within the DES itself, that is, DES provides cooling to the building, or within the connected buildings, that is, DES provides heating to the building converts heating to cooling. When the equipment that converts DES supplied heat into cooling is part of the LEED project's scope of work, the DES guidance is modified as follows. Model the district heating source servicing the chilled water generation equipment as follows. 1. For Path 1, use purchased heat in both the baseline and proposed cases. 2. For Path 2 or 3, use a virtual upstream DES plant for the proposed case and compare it with code-compliant on-site equipment for the baseline case. For Path 1, model absorption chillers in the baseline case as follows. 1. When the purchased heating is hot water with average supply temperatures below 300 degrees Fahrenheit, 148.9 degrees Celsius, the chillers must be modeled as single-effect absorption chillers, 0.7 COP. 2. When the purchased heating is steam or hot water with average temperatures greater than or equal to 300 degrees Fahrenheit, 148.9 degrees Celsius, the chillers must be modeled as double effect absorption chillers, 1.0 COP. 3. If the building peak cooling load is less than 300 tons, 1050 kilowatts, model 1 water-cooled absorption chiller. 4. If the building peak cooling load is between 300 tons, 1050 kilowatts, and 600 tons, 2100 kilowatts, model 2 water-cooled absorption chillers, sized equally. 5. If the building peak cooling load is more than 600 tons, 2100 kilowatts, model a minimum of 2 water-cooled absorption chillers, with chillers added such that no chiller is larger than 800 tons, 2800 kilowatts, all sized equally. 6. For a project with both absorption chillers driven by purchased hot water and electric chillers on site, the type and quantity of absorption chillers must be as identified above, and the type and quantity of electric chillers must be as in Table G3.1.3.7, or DX equipment as specified, but the total capacity ratio of electric to absorption cooling must be identical to that of the proposed design. 7. For a project including both district chilled water and absorption chillers on site driven by purchased heating, the type and quantity of absorption chillers must be as identified above, and purchased cooling must also be modeled in accordance with the district energy modeling guidance. However, the total capacity ratio of the on-site cooling to purchased cooling must be identical to that of the proposed design. Model the baseline case cooling towers, pumps, chilled water loop configurations, and loop temperature controls as indicated in Appendix G. Model the absorption chillers in the proposed case based on the as-designed type and capacity of chillers. Other atypical systems. DES also often incorporate unconventional features, such as thermal storage, ground or surface water cooling, and waste heat recovery. These features should be incorporated into the proposed virtual plant to the greatest extent practical using the general principles presented in this guidance. International tips. Whole building energy simulation. If ASHRAE 90.1 is not applicable, requirements can be met with a USGBC approved equivalent standard. Consult ASHRAE/ISNA Standard 90.1 to 2010, Appendices B and D, to find the project's climate zone. Use Table B2, Canada, or Table B3, International, if the location is listed. For locations not listed in Table B3, use Table B4, along with the climate type definitions in Section B2, plus Appendix D to determine climate zone. For example, a team working on a project in Beijing consults NC/ASHRAE/ISNA Standard 90.1 to 2010, Appendix B, to determine the appropriate climate zone. Table B3 does not give a climate zone for Beijing. The project team finds Beijing in Table D3, which lists the values for heating degree days to base 65 degrees Fahrenheit or 18 degrees Celsius, HDD 65 or HDD 18, as 5252, and cooling degree days to base 50 degrees Fahrenheit or 10 degrees Celsius, CDD 50 or CDD 10, as 4115. The team uses these values to determine Beijing's climate zone as defined in Appendix B, Section B2 and Table B4. Beijing is in a moist climate because its warmest month has a mean temperature higher than 72 degrees Fahrenheit, 22.2 degrees Celsius, and is therefore too warm to be a marine climate, and annual rainfall data indicate that the city is not in a dry climate. Finally, the project team uses the values found in Table D2 for HDD 65, 5252, and CDD 50, 4115, in Table B4 and determines that Beijing is in Zone 4A, mixed humid, because the CDD 50 value is 4500 or less, and the HDD 65 value is between 3600 and 5400. Related credit tips. EA credits. The EA prescriptive credits include specific measures that will improve the home's energy performance. EQ credits. The EQ credits include strategies to maximize building performance and may produce either trade-offs or synergies with EA credits. For example, HVAC distribution systems affect both indoor environmental quality and the energy efficiency of a home. EA credit annual energy use. A home with a HERS index lower than the reference home is eligible for additional points. Changes from LEED for homes 2008. Homes, the reference to Energy Star standard has been updated from version 2 to version 3, which substantially increased energy efficiency, comfort and durability performance of the home. Additional prescriptive requirements have been included, such as requiring that at least one Energy Star qualified refrigerator, dishwasher or clothes washer be installed in each dwelling unit, and that all duct runs must be fully ducted. Multifamily mid-rise. The standard has changed from 15% above ASHRAE 90.1 2007 to 5% above ASHRAE 90.1 2010, a roughly 10% increase in stringency. Contract language recommendations. Builder, construct a home that meets Energy Star, version 3V performance requirements with third-party verification. Ensure compliance with all requirements of the Energy Star thermal enclosure system rater checklist and deliver the completed water management system builder checklist to the HERS rater. Any work determined by HERS rater to not meet requirements of Energy Star, version 3, will be corrected promptly at builder's expense. HVAC contractor, design and install a heating, cooling, and ventilation system that meets Energy Star, version 3, requirements. Design the system to enable third-party performance verification. Provide the HERS rater with the completed HVAC system quality installation contractor checklist. Any work determined by HERS rater to not meet requirements of Energy Star, version 3, will be corrected promptly at contractor's expense. Technical resources. Energy Star, version 3, training materials. EnergyStar.gov. Energy Star product specifications. EnergyStar.gov web link. Referenced standards. 2006 Mortgage Industry National Home Energy Rating System Standards. ACA Manual D, Residential Duct Systems. ACA Manual J, Residential Load Calculation, 8th edition. ACA Manual S, Residential Equipment Selection. ASHRAE 90.1 to 2010. Energy Star Qualified Homes, version 3, National Program Requirements. Energy Star Qualified Homes, version 3, Inspection Checklists for National Program Requirements. Energy Star Multifamily High-Rise Simulation Guidelines. Energy Star Multifamily High-Rise Testing and Verification. Multifamily Mid-Rise Thermal Enclosure Inspection Checklist. ComNet Commercial Buildings Energy Modeling Guidelines. USGBC's Residential Multifamily Mid-Rise Simulation Guidelines. Exemplary Performance. Not available. Verification and submittals. Supporting verification materials, made available by the project team. Homes. Provide Energy Star for Homes label or certificate, if applicable. Provide details on Energy Star label for refrigerator, dishwasher, or clothes washer. Group project. Worst case energy models following USGBC and EPA protocols may be performed for specific units in multifamily buildings. Verification team. Homes. Conduct on-site verification of all required Energy Star for Homes inspections. Upload Energy Star for Homes inspection checklists. Upload Energy Model file. Upload Energy Star for Homes PDF report demonstrating that project meets Energy Star for Homes requirements, or upload Builder's option package to demonstrate compliance with prescriptive Energy Star for Homes requirements. Glossary. Baseline building performance. The annual energy cost for a building design, used as a baseline for comparison with above standard design. Charrette. An intensive, multi-party workshop that brings people from different disciplines and backgrounds together to explore, generate, and collaboratively produce design options. Enclosure. The exterior plus semi-exterior portions of the building. Exterior consists of the elements of a building that separate conditioned spaces from the outside, that is, the wall assembly. Semi-exterior consists of the elements of a building that separate conditioned space from unconditioned space or that encloses semi-heated space through which thermal energy may be transferred to or from the exterior or conditioned or unconditioned spaces, for example, attic, crawl space, basement. Renewable energy. Energy sources that are not depleted by use. Examples include energy from the sun, wind, and small, low-impact, hydropower, plus geothermal energy and wave and tidal systems. Hardscape. The inanimate elements of the building landscaping. It includes pavement, roadways, stone walls, wood and synthetic decking, concrete paths and sidewalks, and concrete, brick, and tile patios. Adjacent site. A site having at least a continuous 25% of its boundary bordering parcels that are previously developed sites. Only consider bordering parcels, not intervening rights of way. Any fraction of the boundary that borders a water body is excluded from the calculation. Assembly. A product formulated from multiple materials, for example, concrete, or a product made up of subcomponents, for example, a workstation. Density. A measure of the total building floor area or dwelling units on a parcel of land relative to the buildable land of that parcel. Units for measuring density may differ according to credit requirements. Does not include structured parking. Occupied space. Enclosed space intended for human activities, excluding those spaces that are intended primarily for other purposes, such as storage rooms and equipment rooms, and that are only occupied occasionally and for short periods of time. Occupied spaces are further classified as regularly occupied or non-regularly occupied spaces based on the duration of the occupancy, individual or multi-occupant based on the quantity of occupants, and densely or non-densely occupied spaces based on the concentration of occupants in the space. Infiltration. HVAC, uncontrolled inward air leakage to conditioned spaces through unintentional openings in ceilings, floors, and walls from unconditioned spaces or the outdoors caused by the same pressure differences that induce exfiltration. ASHRAE 62.1 to 2010. Downstream equipment. The heating and cooling systems, equipment, and controls located in the project building or on the project site and associated with transporting the thermal energy of the district energy system, DES, into heated and cooled spaces. Downstream equipment includes the thermal connection or interface with the DES, secondary distribution systems in the building, and terminal units. Drift water droplets carried from a cooling tower or evaporative condenser by a stream of air passing through the system. Drift eliminators capture these droplets and return them to the reservoir at the bottom of the cooling tower or evaporative condenser for recirculation. Upstream equipment. A heating or cooling system or control associated with the district energy system, DES, but not part of the thermal connection or interface with the DES. Upstream equipment includes the thermal energy conversion plant and all the transmission and distribution equipment associated with transporting the thermal energy to the project building or site. Combined heat and power. An integrated system that captures the heat, otherwise unused, generated by a single fuel source in the production of electrical power. Also known as cogeneration. Adapted from U.S. Environmental Protection Agency. Process energy. Power resources consumed in support of a manufacturing, industrial, or commercial process other than conditioning spaces and maintaining comfort and amenities for building occupants of a building. It may include refrigeration equipment, cooking and food preparation, clothes washing, and other major support appliances. ASHRAE. Thank you for watching. Watch for the next video. LEED V4 Homes, EA Prerequisite 2. Energy Metering. If you wish to get the PDF or PowerPoint copy of this presentation for free, please click the link below or email me at nelca_roco@yahoo.com.